All right, hi there, folks. So as you talked about, today is going to be a video lesson because I am not here. So your warm-up is going to be at the bottom of page 4, same notes as Friday, problem 3, part B. So I'm going to tell you to pause the video, try it on your own for 4 minutes, and then you can unpause and then I'll go over the problem. All right, so this should be playing again after those 4 minutes, presuming that you've done the problem, maybe talk to some people. But let's go over how to graph g of x. So I want to find the roots of all of these factors. And that, in this case, means that we're going to have to factor a little bit more. So x squared minus 4 could be factored as x plus 2 and x minus 2. We still have another x minus 2, right? So the first x minus 2 coming from our x squared minus 4 when we factor it, but there was still one right next door. 2 of those. And then factoring here, x squared plus 5, x squared, what am I saying, x squared? X plus 3 and x plus 5. That seems right. So that would give us x plus 2, x minus 2 squared, x plus 3, and x minus 5. Right, and then breaking down roots and multiplicities, -2, 2, -3, and 5. Multiplicities of 1, 2, 1, 1. So cross, bounce, cross, cross. All right, I can see right here that there are 5 roots in total, right? 1, 2, 3, 4, 5. Even though we have 4 numbers, we're using 2 twice, so that's 5 in total. So odd degree looks like it is a positive lead coefficient. So tails looking like this, and then we can write out the end behavior. As x approaches infinity, g of x approaches infinity. As x approaches negative infinity, g of x approaches negative infinity. Right, so the first sentence representing the right-hand tail, the second sentence representing the left-hand tail. Right, so now I can go ahead and graph. Let's see, the greatest number I need is 5. Scaling out the axes and then drawing in the intercepts. Again, make sure that you are labeling your intercepts and make sure that those are all labeled. Look back at your end behavior, right? We know how our tails are supposed to look. Go ahead and draw those in. Right, and then we will just cross, cross, bounce. Just make that just a little bit deeper in the middle. There we go. I feel good about that. All right, so then where g of x is greater than 0, is where the function is above the x-axis. So -3 to -2, union 5 to infinity. And then where g of x is less than 0 would be where the function is below the axis. So -infinity to -3, union -2 to 2, union 2 to 5. right, so I don't know if you are watching this as a class or if you're watching this individually. If you're watching as a class, just talk to a neighbor and just make sure that y'all are good after this. Or if you're watching individually, then don't do that because you may not be at the same point in the video. Either way, I'll give you a moment to check on the screen or pause if you want to, and then we'll move along. All right, let's get on to writing polynomial functions. So we're going to start with problem 4. You have a graph on the right. We know that the function g of x is degree 4, and we will have to write a factored form equation representing g of x. All right, so first thing I'm doing is looking at the intercepts of the function, the roots of the function, right? We've got an intercept at x equals 5. We can see that there's a bounce, right? An intercept at x equals 0 and an intercept at x equals -3. All right. If you set all of these values equal to x, right? You could do that to figure out what the linear factors are going to be. Now, we've done this in quadratics, and you may be able to just like sort of, make the jump straight into the factors in case that was a little touch and go for you. If you have x equals -3, right, then we can just add 3 and say that our factor is x plus 3 equal to 0, right? That's how we're using the zero product property. This is already set up for us. And then in this case, x minus 5 is equal to 0, right? This giving us a factor that we could use for the zero product property. Right, so with those factors, we could write out g of x is equal to x plus 3. I'm going to put the x out front. I usually like the x, just the normal plain old x to be out front. And then x minus 5 would be our last factor. There needs to be a bounce. So we need an even multiplicity, even exponent on the factor. And if we do that, then we will have our degree 4, right? There's 1, 2, 3, 4 roots. So we're meeting our degree 4. Right, but one of the reasons why there's so much white space down here is because just like in quadratic functions, you will need to find an a value. Right, so I'm going to put that here, and I'm going to write it over here, and you should probably write it on yours. Find the a value. Right, that is an expectation, particularly when you're given enough information to do so, and we have enough information here. Right, if you are given an ordered pair, for any point besides an x-intercept. We cannot use an x-intercept for this process, but if you have any other point, you can find the a value, and you should find the a value. It is an expectation. All right, so 30 in for y, 2 in for x, right? And the rest of the equation stays the same. This is very similar to what we were doing with quadratic functions, right? Very similar. So 30 for our y value, 2 for our x value. The rest of the equation is all the same. All right, so we can go ahead and start simplifying. So 30 is equal to a times 2 times 5 times -3 squared. Notice I'm using parentheses here. I can put the 2 and 5 together and make 10. This could be 9. And then it's not too bad if you multiply 10 and 9 together to make 90, because 30 over 90, that's not too bad. But there are times where that reduction in that division will get more difficult. So one of the things that I encourage you to do, I do it all whenever I'm doing these processes, is not necessarily multiply all of these coefficients together, because you're going to have to refactor them back out in order to reduce. It might be easier if we just divide off factors individually, right? So if I divide off 10, I'll get 3 is equal to a times 9, right? And then a is equal to 1/3, right? Not too bad when it's 30 over 90, but if it was, for example, 24 over 72, you're like, wait, hold on, 24 over 72, you'd get there, but it would take you just a little bit longer. So if you just leave things factored out and start dividing out factors, the numbers won't get as intense, in my opinion. But a is equal to 1/3. right? And as we talked about before, this is not the final answer, right? That is part of the final answer, but you were told to write the factored form equation. So that is what you need to provide. Right, g of x is equal to 1/3 times x plus 3, x minus 5 squared. Right, there we go. We can also do this writing process if we aren't given a graph. We could be given a table. So let's take a look at this. Right, polynomial function f of x degree 4 in the table, and we have to write in an equation. So similar to how we did with the graph, the first thing I'm looking for are the roots of the function. Right, the roots of the functions being found at the x-intercepts where y is equal to 0. Right, so we'll notice that y is equal to 0 at these points. Right, f of x representing y, f of x equal to 0. These are our x-intercepts. Right, so I might be seeing a factor of x plus 7, or a factor of x plus 2, a factor of x minus 4. Right, but look at this, it is degree 4. We have 3 factors, 3 roots at the moment, right? Something's missing here because it's not lining up with our degree 4 for this polynomial, right? I'm telling you right now, one of these intercepts is a bounce. 2 of them are crosses, one's a bounce, right? Think for a moment, how might you figure out if an intercept is a bounce or a cross if you don't actually see the graph? The answer is by looking at the points around the intercept. If we have a negative y value on one side of the intercept and a positive y value on the other, right, then we have to physically cross the axis to go from negative y values to positive y values, right? So that's how we know that this intercept is a cross. Right, if we start with positive y values and end with positive y values on the same side of an intercept, right, positive hit the axis positive, that creates a bounce at that intercept. That's how we know that this intercept is a bounce. And this sign change, as we talked about, represents a cross. Right, so we have 3 intercepts, but the 4 roots are coming from that doubled multiplicity at x equals -2. Right, so I can put these factors together here. Definitely f of x, right? But as I told you, if you're given enough information to find the a value, you absolutely need to, and you're given more than enough information because you're not just given one ordered pair like up here. We literally have like, what is this? 1, 5, 10, you got like 12 more ordered pairs, right? Take your pick. Again, the only rule is that you cannot use an x-intercept because that's already represented in the function, right? We have to find a different point to use. Now, I am not necessarily a fan of getting stuck on like always use the y-intercept for the reason of, if we look right here, like I don't really want to deal with a 112. It's kind of big, frankly. I think a -130, a -328, those are nice. It's not 0 with our x value, but these numbers are nice. I think they're a little smaller, easier to work with. So you can do this. I'm not telling you not to, but me personally, I would pick, let's go with -130. I think I like that for what we're doing here. All right, but in a table, you really do have your pick of what points you're going to use. So 30 again in for y. -1 for all of our x values. And we'll keep the rest of the equation. Right, and now it's time to solve. So 30 is equal to a times -1 plus 7 is 6. -1 plus 2 is 1, squared is 1. I don't really want to write that out. Multiplying by 1 doesn't really do anything for my equation. So 30 is equal to a times -30, or -1 is equal to a. So I have our equation, an A value, we just need a negative. And we're good. All right, so again, go ahead and pause this video if you want to take another look at this problem. The solution all worked out. But otherwise, we will go ahead and advance. I'm going to go past 6, and I think you can double back for it having done 5. I think you can do that sort of on your own. 7, I also think you can do on your own. I want to move on to problem 8. And so the function f of x is shown in the accompanying graph. These intercepts are not labeled, but I think we can figure out what those are. These maxima are labeled. Doesn't look like we'll need that for the A value. Those decimals are pretty gnarly. But an extra point, I think that might be useful for an A value. But it looks like before we write the equation, we do have to find the following intervals. So just refresh on that. I'm actually going to tell you to pause the video and just try this on your own for a moment. And then once you just made a real attempt at this, then you can unpause and I will go through those answers. All right, so at this point, I think you have unpaused. So let's go ahead and go over some of these intervals where f of x is greater than or equal to 0, right? Greater than or equal to. So all of this being greater than, right? The curve is above the axis. Same story over here. And same after we get past this intercept. Right? But because our inequality says greater than or equal to, we are also going to include these intercepts, right? Because f of x is equal to 0 at those points. So really, I think this is just -2 inclusive onwards to infinity, right? We're going to include -2 right here and every x value after that. So -2 to infinity. If we want the negative interval, our curve is below the axis all the way over here. Right, I'll draw the tail on. That's going to keep going down and down and down. It's like -infinity to -2 exclusive, right? Because again, the difference between this condition and that condition is that with this inequality, our y values can equal 0. If we're saying just straight positive, negative, 0 is neither positive nor negative. So we don't want to include a point where y is equal to 0. Right, our increasing sections. Would be right there. So the first section on the left, -infinity to that x coordinate of -1.452 union. We pick up at 0 and then go to 1.652 union 3 to infinity. Right, remember, we are using the x values to write our intervals. The y values help us figure out if we have met the condition, but we are using the x values to write the interval itself. All right, and then our decreasing sections from maximums to minimums. Be right there. Looks like -1.452 to 0 union 1.652 to 3. And another reminder, we are using parentheses for the increasing, decreasing intervals because at the maximum, we are neither increasing nor decreasing, and the same is true at the minimum. Positive and increasing. I'll go blue. It's about to go green, but I'll color code differently. Positive increasing be those sections of the graph. So I want sections of the graph where we are above the x-axis and increasing at the same time. That honestly looks like the same answer as this question, but instead of starting at negative infinity, we're starting at -2. And then for negative and decreasing, I don't think that interval exists, right? We only have this negative section, right? Negative infinity to -2, this part of the graph down here. But this entire section is increasing as we move left to right, right? So even though the tail is pointing downwards, the increasing, decreasing is traced left to right. So if we go left to right, it's always going to keep climbing up and up until it hits, right, this intercept or this maximum, depending on how you're looking at it. So I don't think there is an interval that fits this criteria. So NA. Right, but now we have to write an equation representing f of x. All right, so we've got intercept at -2, intercept at 0 with a bounce, and intercept at 3 with a bounce. Right, and make sure that you're looking at the scaling, looking at the labeling, and not just counting off tick marks from the grid. Right, f of x is equal to, we'll have to find an a value. That bounce at 0 would come from a factor of x squared, x plus 2 for a root of -2, and x minus 3 squared to account for that bounce. Right, the ordered pair that we're going to use here is 2, 6. So 6 in for our y value, 2 in for the x's, right, everything else stays the same. So 16a is equal to 6, or a is equal to 6 over 16. Reducing by 2 would be 3/8. So final answer, f of x is equal to 3/8 x squared times x plus 2 times x minus 3 squared. All right, let's move on to the last problem that I'm going to do with you here, problem 9. So the x and y intercepts of the polynomial function f of x are shown below, and these are the points that you see on those axes. So we'll need to complete the graph of f of x, write the end behavior for f of x, and then write an equation for f of x. Right. One thing I'm going to point out here is that you may look at these and be like, are these bounces? Are they crosses? Is it up to me? I don't know. It's actually kind of decided for you, because when there is an even multiplicity, you'll see an E or a B for bounce. You could probably go either way. But if the intercept is unlabeled with any of that extra business, then you have to treat it as though it is a cross, which is a multiplicity of 1. Right, so anything unlabeled like this, multiplicity 1, and we're going to cross anything else, right? That's where we're going to incorporate all the higher degrees. Right, so there's like 5 points. They have to be connected by a curve. And I wouldn't necessarily just start at one end and start moving through, because, you know, for example, let's say that I did something like this, right? It just came up and then down, and then hold on, right? Once you get down here, you're going to be like, well, I have to get back up to this y-intercept. And then you would cross through and hit the y-intercept, except now you've created an intercept right here that's not supposed to be there, right? There was no x-intercept labeled at this point. So how are you crossing the x-axis to get back up here? right? So then you might say, okay, well then I'll reverse, right? And I'll come down and then back up. And now I can hit the point and back down, right? Which like works, but at a certain point, you're just guessing and checking, right? What I would say is pick your point or find your point that has to be off of the x-axis, right? Start here, then work out to the sides, right? And all connect together as a continuous function, right? If I start with this y-intercept and I come down and I hit this x-intercept, I'll cross, bring it back, cross and draw on the tail, right? And then I'll come back to the y-intercept, hit that x-intercept, come back, hit there, bounce off for the even multiplicity, and then continue drawing down. Right. Also, is this minimum actually at y equals negative 25-ish? Really no way to know. So if you know, or rather there is a way to know, but you need a calculator or calculus. We're not going to do either of those right now. So don't get too hung up on the vertical scaling. I would say the horizontal scaling is more important when there's a grid provided. If the grid wasn't here, then I think we would have an easier time with it. But as long as you're following the bounce cross, as long as this passes the vertical line test, and is a function, things are in the right order. I think for a problem like this, where you're connecting the dots that were given to you, I think that would be sufficient. All right, so let's write some end behavior for f of x. I'll write the left-hand end behavior first. So as x approaches negative infinity, right? And we always are going to start with that phrase when we were describing the left-hand end behavior, the left-hand tail. F of x is approaching infinity, right? The tail is pointing upwards. Our right-hand tail, you can see that f of x is going lower and lower, y is pointing down. So as x approaches infinity, then that's the phrase for our right-hand end behavior. F of x is approaching negative infinity. And now we need to write an equation representing f of x. So f of x equals, we have a y-intercept off the x-axis, so that is enough for an a value. We have a root of -4, so a factor of x plus 4. A root of -2, I want an x plus 2. Root of +1, x minus 1. And then a root of +4, so x minus 4, but we saw that there was a bounce. So build in that multiplicity of 2. Right, using our extra point up here, 0, 64, I can sub in for the y value, 64, and the x value being 0. And everything else, as it does, will stay the same. All right, so 64 is equal to a times 4 times 2 times -1 times -4 squared would be 16. Right, and to reiterate, I am not particularly interested in multiplying 4 times 2 times 16 and getting like 96, and then, okay, what's 84 divided by 96? Like, it's too much. It's too much, right? I just want to divide things while it is in factored form, and let's see where that gets us, right? So if I divide off the 2's, this would become 32, right? So now 32 is equal to a times 4 times -16, right? Okay, let me do that again. Let me divide off the 16's. That would leave me with a 2, right? Dividing this side by 16, dividing that side by 16, right? So 2 is equal to a times -4, right? Or, at this point, if you want to write that out, I think that's fine. A times -4. If we divide off -4, we'll see that a is equal to -1/2. Did I say 96? I think I just pulled that number out of thin air. The right-hand side, all those coefficients would not equal 96. But you know what? I think that just goes to my point that you should just keep things factored and divide off the factors as opposed to trying to get cute and multiply all those numbers together. Actually, yeah, 8 times 16 would be, it's not 128, is it? All right. The whole business with the, writing the factors and plugging in x, y to solve for a, I mean, that's just an extension of the quadratics from unit 2. I would say for y'all, for some of you, it's going to be a push to break out of the habit of constantly trying to multiply these things together. Like, to borrow a phrase from another math teacher, Ms. Rankin, don't be a robot, right? Don't be a robot where you just like algorithmically, just out of habit, keep multiplying things together because you think that's what you're supposed to do. Like, I would say this, if you have enough stuff going on here, like enough factors being multiplied together, get comfortable just dividing those off one at a time. There's no need to multiply these together, just to divide it over and then have to refactor it so that you can reduce it. Just divide one factor at a time, and that'll get you to the A value that you need. All right, so there's our final answer. All right, so you've got a bunch of blank problems in here. You got problem 10. Like, come back up here, you've got problem 7, problem 6. If you didn't finish the graphing problems, like those problems, I would say go back and do those. That is what you will need to do for the rest of class time. And then make sure that you submit your completed notes into the Canvas assignment by the end of the period. You don't necessarily need to have all of the problems completed, right? But I do need to see evidence that you were doing something while I was gone. All right, so hopefully this went well. You still have access to the video if you want that after class, and I will see y'all tomorrow. Bye-bye.